Oh, okay, sir. We can start, sir. Hello, are you
Sure.
there? Yeah.
Yeah, I'm
Okay.
here. Yeah,
Yeah.
please.
Okay, sir. Yeah.
So,
Just for what? 2 minutes.
1 minute.
Okay. A very good morning to one and all. So this is the session 5. So going to the particular session 5, let's introduce our speaker, Dr. Ambika Prasad. Reliability and security issues in VLSI circuits and systems. So let me introduce first. Dr. Ambika Prasad sir is currently working as an assistant professor, electrical engineering department and associate dean, corporate relations at IIT Jammu, India. He received PhD degree from the Electrical Engineering Department, IIT Indore, India. Before joining IIT Jammu, Dr. Shah worked as an postdoctoral fellow at the Institute for Microelectronics, TU Vienna, Austria. He is the recipient of Young Scientist Award from MP Council of Science and Technology Bhopal, MP India. He has authored and co-authored more than 55 research papers in peer-reviewed international journals and conferences. He is the fellow of IIT, senior member of IEEE, and the lifetime member of IST, ISCA, IEI, and IAENG. His current research interest includes reliability analysis of digital circuits, design for reliability, fault-tolerant circuits, reliability modeling, low-power, high-performance circuit designs, and IoT secured circuits. So it is a nice biography, sir. And in the meantime, your research interest area also includes many fields. So you are most welcome to the particular session, sir. So you can start the session, sir. Dr.
Okay,
Ambika,
so
sir.
thank you so much for the nice introduction, and thank you for inviting for the talk in FDP. So let me share my screen first, then we can
Yes, sir.
start. Okay, so 1 minute. Actually, I am actually.
Sure, sure, no problem.
I think now you may be able to see my screen, half screen, right?
Yeah, it's
Okay,
yeah,
so I'm making it full screen, then we
full
can
screen. Yeah,
start. Okay,
yeah,
so thank you so much for the invitation. And the title of my talk would be related to reliability and the security issues in VLSI circuit and systems. And yeah, of course, this is really a very good FDP, which is conducted from the support of Atal Academy. And before going into the start of main content, let me introduce what kind of content I am going to cover in this particular talk. So basically, I will start from the reliability issues, which consist of PVT variations, bias temperature instability, hot carrier injection, then time-dependent dielectric breakdowns, aging effects, and then software. So these are some reliability issues with the nanoscale technologies. And then I will talk about something hardware security issues, I will talk about the hardware security primitives, like physical uncontrollable function, TRNG, counterfeiting electronics, hardware trojan. So, and then I will talk about what kind of different reliability research challenges are there, what kind of work we can do, and what kind of works are unexplored, which we need to consider. And then I will talk about some security challenges, especially for secure applications. And then I will talk about what are the different challenges and what are the different research gap which we need to consider before moving into the research side. So this particular talk will be completely related to the research gap, different problems associated with the reliability and the security of the systems and the circuits, and what kind of problems are unexplored, that will be discussed. And might be you will be able to get some of the idea or some of the research direction from where you can start working towards the reliability and the security side. So this is all about the content. Now let me start my the talk with the introduction. Like, as we know that the technology is scaling down, the IC feature size has been driven into many physical limitations. So there are many scaling techniques, like we talk about the constant field scaling technique, constant voltage scaling technique. But if I want to increase the device density in a single chip or in a unit area, so the one of the possible way is to reduce the size of the transistors. But directly we cannot reduce the size of transistors. So with the miniaturization of the transistor or with the scaling down of the transistors, definitely there may be some secondary effects that comes into the picture, and that may affect the performance of the devices. So we cannot directly decrease all the dimensions with some factor, and that the device will work according to our plan. It's not like that. So we need to consider some other secondary effects which comes after scaling the devices, and that need to be considered while designing the circuit or the systems. Okay, so as we know that device scaling reduces the oxide thickness by around 30% in each next technology generation. So because if the oxide thickness is reducing by 30% in each technology generation, maybe this kind of the scaling of the oxide thickness may create the tunneling of charge carriers from one terminal to another one, right? And because of this, the reliability and the variability issues are the biggest design challenge facing, especially at the nanoscale high speed. In order to keep a technology scaling down, we need to consider two major things. The first one is the excessive leakage power dissipation, and the second one is the circuit reliability or the device reliability. Because definitely we are making the circuit based on the devices. So if the device is reliable, then we can make the circuit. We can also make the circuit reliable. Okay, and of course the system will also be the reliable. So we have to start from the scratch, like the device reliability. Even though if you can go into the more deep, like you can have some materials which is more reliable, which is giving better performance as compared to the other one in terms of the reliability. So we can start from the material, then we can go for the device designing, then we can consider the circuit architecture which is having the better reliability, and then we can talk about the systems. So yes, of course, we can consider the reliability in any of the hierarchical structure in the VLSI domain, which starts from the material to the system. Okay, and if we consider the PVT variations are the serious issues in the skilled technology, so definitely we need to consider these PVT variations. Apart from these PVT variations, because these PVT variations are like, time independent variations, but there are certain reliability mechanisms which can affect the performance of the devices or the circuit with respect to time. Those kind of reliability issues are known as the temporal degradations. Okay, and if you consider temporal degradations, there are basically three kinds of temporal degradations. The first one is bias temperature instability, which is generally we call it BTI. Second one is hot carrier reaction, and the third one is ambient dielectric breakdown. I will discuss one by one each of these, because my main focus will be towards to the temporal degradation. So I will take more time to explain these temporal degradations and how they can perform, how they can affect the performance of the circuit and the devices, and subsequently system performance. Temporal degradations and the PVT variations, there is one more vulnerability which we call like soft error. So if we are operating our device or our system or our circuit into the harsh environments, like where the presence of high energy particles are more, in that case, the soft error becomes also one of the prime concern, especially for the space applications or the aerospace applications. So these are some of the points or some of the terms which we need to consider if I am targeting the reliability concern of any devices, circuits, or the systems. Okay, so I will talk. Okay, if yes, apart from this, like reliability issues, as you see from the title of my talk is related to the reliability and security both. Some of the terms which come under the reliability that can also be considered while considering the security circuit designing. Okay, how we can consider reliability concern while designing the security circuit, I will tell you in the details later on. Okay, So there are basically three edges of the circuit and system resilience. The first one is the integrity, second one is availability, and the third one is the confidentiality. Okay? And if we talk about the integrity,
Excuse me,
we can
sir.
have, yeah, please.
So actually, there is comment that something breaking in your sound. Can you check once voice is breaking and something
Oh.
resound maybe?
Okay, let me.
Yeah, no problem. You can continue. Just check it once.
Now it's fine.
Yeah, fine. It's fine.
Are you getting my voice proper? Okay, perfect.
Okay,
So
continue.
basically, yeah. So the circuit are divided into three edges. First one is integrity, second one is the availability, and the third one is the confidentiality. If we consider the integrity of any circuit and system resilience, in that case, the integrity is divided into two parts. The first one is like internal interference, process variation, and the environmental noise. So these kind of the resilience, these kind of the problems are generally considered under the reliability effect. Or if I want to make our device or our system more reliable in terms of the integrity edge, then I have to consider the device or the circuit should be having the less process variations. It must have less environmental noise effect, and the interference of the devices or internal interference should be as low as possible. So if we can meet all these three criteria, then we can consider like the integrity of the system or the circuit is better considering the reliability perspective. Similarly, if we talk about the security perspective, then the hardware tampering, accelerated aging, fault injection, these all considered under the integrity side. Similarly, for the availability, fault, permanent fault. So if we can avoid these kind of faults in a circuit and system, so we can say that the availability of faults are very less, or there is no availability of fault. So we can call it like the system is more reliable in terms of availability. Okay, or in the edges of the availability. Similarly, if we consider the security perspective, in that case, we need to consider control flow. In the service, if there is some attack, we need to
Pardon, sir. Excuse me, sir.
Yeah.
Ambika, sir. Sir, actually,
Yeah,
voice
please,
is
I'm
breaking.
getting it. Oh,
The voice is breaking, sir. In the chat box, also participants are saying. Also, I've also marked that voice is breaking. Can you check the network once, sir?
Yeah,
Like it up and down voice.
Yeah, please.
Yeah, just you can check once. Yeah.
And network is also good.
Maybe network issue.
Yeah. So 1 minute. Please give me 1 minute.
Sure.
I think now you may be able to hear properly. Are you able to hear?
Yes, sir. Now it's clear, sir.
Okay, thanks. Okay, so
Yes,
let me
sir.
make
Continue.
it fully seen again. Okay, so I was talking about the availability. So here we can consider the reliability as well as the security concern, considering the edges of availability. And the third edge is the confidentiality. So basically, if you consider the confidentiality, in that case, side channel attack, hardware tampering, Trojan insertions. So Trojan insertion and hardware tampering means if we are playing with the chip without information of the foundry, or we have added some unwanted section in the in while designing. So these kind of things are comes under the confidentiality. So these are the some of the concern while considering the resilience edges for circuit systems. Okay. Now, if I talk about yeah, definitely, because if you can see here, some of the terms are common in integrity, like we can consider it for the reliability and the security both, and similarly for the availability we can consider the reliability and the security. So there is some common thing which we need to consider while designing the system and the circuit, which should be reliable as well as secure. Okay, so how we can combine these two things, I will tell you later on. Okay, now let us go through some details of the reliability failure mechanisms. You all know all these things. So I will go through it quickly. So basically, reliability failure mechanisms are divided into two categories. The first one is time zero, and the second one is time dependent. And the time zero is we can further divide into two categories. First one is the intra-die and the inter-die. And the intra-die, we can have the random dopant fluctuation, line edge roughness, line width roughness, and oxide thickness variations. So these all kind of variation we consider generally intra-die variations. Okay. So here we can see these all kind of variations are known as intra-die variations. Similarly, if we talk about the global variations, so we can have the lot-to-lot variation, wafer-to-wafer variation. So we will discuss all these things in the detail. Similarly, the most important thing is, like, most of the people know how this local and global variation works and how we can avoid in while circuit designing. But the time-dependent variabilities are really very important, and that need to be considered. Which is divided into two categories. The first one is the environmental one, and the second one is the aging effects, where the aging effect is really a serious concern, because if we are operating our device for the longer time, so might be the performance will not be same as before. So the performance start decreasing with respect to time, and we need to consider those concerns while designing the circuit and the systems. So the most important things are like bias temperature instability, hot carrier injection, and the time-dependent dielectric breakdowns. Okay, and similarly, if we talk about the environmental one, so the voltage and the temperature variation is well-known variation effect, and one of the variation effect is the soft error, especially where if we are operating our devices or our system in harsh environments. Okay, and similarly, electromitigation migration is one of the concern if we consider the backend side. Let us discuss one by one quickly. Like the first start with the global variations. So we can have like the intra-die variations. Intra-die variations means what? If we have the two devices, in that case, if the variation while designing or while fabrication of those devices, if both devices are performing differently, so those kind of variations are known as the intra-die. Okay, and if the variations are, so see, here we have the lot. In the single lot, we can have the different n number of wafers. We can cut n number of wafers, and on n number of wafer, we can have n number of dia. If we can see here on a single block, which we can see here, this is nothing but this is dia. On this single dia, we have to fabricate a chip, or in this particular dia, we have to make our design. But if we have the wafer and we have suppose n number of dia, so each dia may perform differently, because it is not possible that we can expose all the devices or we can fabricate all the devices on a dia on with the same properties. This is only because of the miniaturization of the transistor. Like if we scale down the devices, the performance degradation or these variations becomes higher in the fabrication while fabricating the devices. Here we can have some while to analyze the variations, we can have some to analyze our system or to analyze our circuit performances. We can consider the various process corners, and those process corners are known as slow, fast, slow, fast, fast, slow, and the typical. Okay, where the SS, TT, and the FF are known as the symmetrical one, and FS and SF are known as asymmetrical one. This is because if we talk about the SS, FF, and the TT, both the devices like PMOS device and the NMOS device will change equally. Like so, if the threshold voltage of one of the device is increasing, so the threshold voltage of the other device will also increase. But if we talk about the asymmetrical one, where the fast slow and the slow fast, so one of the device is slow and the another device is fast. So and the vice versa for the other case. So that is why we call them the asymmetrical process corners. If we consider the what is the meaning of these slow process corners? Slow process corner means we need to analyze our circuit in the slow process corners if I have to consider the speed specifications. Like if our device, if our circuit is working perfectly fine, if the device is operating at the slow process corners, so we can say that the device will perform very well in terms of speed specification. Let me say it again what I'm saying. The slow process corner is used to analyze how much slow a device can work, and that can fulfill our criteria. Okay, so if the device is very slow and still it is fulfilling our criteria, so we can call, okay, this is the limit up to which we can consider for the slow process corner. So to analyze the speed specification, we need to consider the slow process corners, and the vice versa for the power specification. So if I have to consider this fast process corner, in that case the power specification will be there. So how it happens? Because if I'm considering the fast process corners, what it means, the threshold voltage of both the devices are low. And if the threshold voltage of both the devices are low, we know the relation. If the threshold voltage is low, definitely the power dissipation will be higher. Okay, so if the threshold voltage of the devices are low and the circuit is working perfectly fine under the limit whatever we have given as per the specification, so we can say that this particular process corner may work fine for the power specification. So this is how it works. So these are the different process corners which we need to consider. Okay, another process variations is like the local variation, which we call it intraday variation, where we need to consider the oxide thickness variation, random dopant fluctuation, and the line edge roughness. So let us start from the oxide thickness variation. What this oxide thickness variation is? As we know that with the scaling down of the technology, the oxide thickness is reduced by 30% in each next technology generation, as I have already told you in the first slide. Okay, so if oxide thickness is reducing, so the atomic layer of this oxide is also going to be reduced. So if there is some variation in the oxide, like let us assume if I have the oxide thickness of 10 nanometer, okay, and if there is some 5% variation, so it could be like 9.5 nanometer, or it could be up to 10.5 nanometer. So the variation range will be 9.5 nanometer to 10.5 nanometer. But if I have scaled down this technology, this oxide layer, and it is up to 2 nanometer, so and if still there is some variation like 5%, 10% variation, so there is a huge variation. This may affect the performance drastically. So, okay, so a small variation in the oxide thickness for the lower oxide thickness, that may affect the performance of the device. Okay, so let me say it again. Suppose I have 10 nanometer of oxide, and if there is some variation of 0.5 nanometer, okay, so that can range from 9.5 to 10.5 nanometer. But if I have the oxide thickness of 2 nanometer and still there is variation of 0.5 nanometer, so the range of the variation will be from 1.5 to 2.5 nanometer, and that variation is too much as compared to the oxide thickness, and this play a major role on the variability. Okay, so this is how the oxide thickness variation play a major role on the reliability. Similarly, if we talk about the random dopant fluctuations, so what happens if I have the older technology, then the number of dopants are very high. But if I have reduced the size of the devices, so the number of dopant will also be reduced. Okay, so for example, for the older technology, let us assume 130 nanometer technology. If let us consider the number of dopants are 1000 atoms per square area, right? And if I have reduced the oxide thickness to, let us assume 16 nanometer, so the number of dopants will be reduced. So per unit area, the number of dopants will be less. So if there is some variation in the number of dopants, just like the oxide thickness, so this can also create the problem. Okay, so the variability in the dopant, number of dopants, will also create the reliability concern. And another one is the line edge or line width roughness. Ideally, we are expecting, if I am fabricating our device, then the device should look like this. Okay, but because up to 130 nanometer technology generation, the wavelength of light which was using for the lithography process was 190 nanometer. Okay, this wavelength of light was used for the lithography process. But still, if we have reduced this technology generation, still we are using same wavelength of light for the lithography. So up to 130 nanometer, there was no as such problems of line edge roughness and the line width roughness. But if we keep on decreasing the technology node lower than 130 nanometer, then this kind of line edge and the line width roughness comes into the picture, and they can create the problem. How they can create the problem? Because the wavelength of light is not matching with the technology node, whatever we are considering. In that case, we are expecting that ideally the gate should be this kind of, but the gate will not be like this. While the lithography, the edges of this line will not be uniform. It will be something like there will be uncorrelation between the two edges. Okay, ideally we are expecting like this, but practically it will not be like this because of mismatch in the wavelength of light while lithography. Okay, similarly, so this kind of problems or roughness are known as the line edge roughness. Okay, and also the width of the whole gate is not uniform, so we can also call it line width roughness. If we can see the figure number 3, third figure, here the line edge roughness is there, but the line width is equal throughout the channel, throughout the gate. Okay, so here we have the equal width. The width is not going to change, but edges are not uniform. There are some roughness in the edges. So the line edge or line width roughness can be of anything, and because of this odd behavior, the performance will decrease. Okay, so this is what the line edge roughness and line width roughness is. Okay, now this is what we call about the process variations. Now let us talk about what is the supply variation and the temperature variation. We know that the delay of any circuit or the gate is given by this one VDD upon VDD minus VTH and some constants. So if I am increasing the supply voltage, definitely the critical delay is going to reduce. But as we know that the power dissipation is directly proportional to the supply voltage. So if I am reducing the supply voltage, we can save the power dissipation. But the problem is we cannot reduce the supply voltage below certain threshold, below certain region, because if I will reduce the supply voltage below some threshold, then might be the delay will be too high, and then system may get failed. So whatever the specification we have, the delay performance requirement we have, if it is exceeding that limit, then the system will be failed. So we need to optimize in terms of delay as well as in terms of the power dissipation. So we need to find some optimum value where we can consider the delay as well as the power, and that particular term is known as the power delay product. Okay, so see, if I am reducing the supply voltage, definitely power dissipation is going to be reduced, but at the same time the delay will also increase, and vice versa. So to find the optimum value of the VDD, we need to multiply the delay of the circuit and the power dissipation of the circuit with respect to the supply voltages, and then we need to come up with one product, that is the power delay product, and the optimum value of the PDP will give you the optimum range, optimum value of the supply voltage where we can operate our device so that we can consider the power dissipation as well as the delay both. Okay, so this is the thing related to the supply voltage. So if there is some small variation in the supply voltage, definitely it is going to affect the performance of the delay, performance of the circuit in terms of delay and also in terms of the power dissipation. Now, one very important thing, like how the temperature variation affect the things. Okay, so the temperature variation means what? Suppose I have a chip. So suppose this is the chip what we have fabricated. Okay, this is the complete chip. But it is not necessary that all the blocks, all the modules present in the chip have the equal activity factor. Okay, might be some of the block have less activity factor, might be this block has very less activity factor, this block having the more activity factor. So we know that if the activity factor is more, then the dynamic power dissipation will be higher. So dynamic power dissipation is higher, then it will generate more heat. So if more dynamic power dissipation, so more hot spot will be created. So if the activity factor, we are increasing the activity factor at certain region, then that region may have the higher temperature as compared to the other regions where the activity factor is less. Okay, so because ideally what we are expecting that the temperature throughout the chip should be uniform, so that all the modules should perform equally, or they have the better means the optimum performance. But the practically this is not possible. This is only because the activity factor of each module is different. Okay, and if the activity factor is different, then what happens if the workload is of any module is going to increases, switching activity will also increase, and if the switching activity is higher, then the power dissipation will be higher. And if more power dissipation, that will generate more heat on that device, and if more heat, then the hot spot will be created. And this kind of variation we call like temperature variations. Ideally, we are expecting that all the modules must have the same temperature, but practically it is not. And what is the reason? I just told you. So we need to design a circuit in a such a way that the module where the activity factor is more must be tolerant to temperature variations. So we need to design those modules with tolerant to temperature variation where the activity factor is higher as compared to the other modules. So by that way, we can maintain the temperature of whole chip. Okay, that could be seen. So yeah, this is what we can summarize. Like if we have the lower process variations, then the delay will be less. And if I have the higher process variations, then delay will be increases. So and similarly, if I'm considering the voltage, supply voltage, so for the lower supply voltages, the delay will be higher. But if I am increasing the supply voltage, the delay will be lower. Similarly, for the temperature, if I have the lower operating temperature, then the delay will be less. But for the higher operating temperature, delay is going to be increased. So we have to consider one optimum supply voltage, optimum temperature, where we can consider, like if you can see here, if I am increasing the supply voltage, so the delay is going to increase, delay is going to decrease. But at the same time, if the temperature is going to increase, the delay is going to is also increasing. So we need to find some optimum temperature, optimum voltages where we can have some better performance. Okay, so this is how this affect like PVD variation affect the delay of any circuit. Now let us talk about the main topic, which is the time dependent dielectric time dependent reliability concerns. Okay, so first time dependent reliability concern is the bias temperature instability. Okay, what this bias temperature instability is? So the bias temperature instability is the time dependent degradation, and that is caused due to dangling bond defect at SiO2 interface. Suppose I have the MOS structure, which you can see in the picture. So what happens? We can have the two kind of oxidation. The first oxidation is like the wet oxidation, and the second oxidation is the dry oxidation. We know these things. Okay, but for the lower technology generation, for better efficiency, we can consider the wet oxidation. So wet for the lower technology generation, wet oxidation is considered to be the better option, or the that performs better as compared to the dry one. Okay, so now the thing is, from where this dangling bond comes. So what happens? Suppose I have some silicon substrate, okay, and I want to make some SiO2 on top of it. Okay, so if I have to make some SiO2 on top of it, so what I need to do? I need to oxidize it. So if I am considering the wet oxidation, in that case, let us assume I am considering the H2O. Okay, so H2 is also there because I am considering the wet oxidation. So some of the silicon atoms will be bounded with the oxygen, and that will make SiO2. Okay, but some of the silicon atom may also bounded with the hydrogen, and because of this hydrogen atom bonding, they will create some dangling bond. They are not as strong as SiO bond. Okay, so this SiH bond is weaker than the SiO2 bond, and these bonds are known as the dangling bond defects. Okay, so ideally there should be no dangling bond. So SiH bond should be as small as possible, but because we are utilizing the wet oxidation, so this SiH bond will also be present. Okay, so now I have some silicon substrate, I have some dielectric material which is SiO2, and then I have some polysilicon which is acting like a metal for the gate terminal. Okay, now what happens if I am applying? So yeah, I will tell you in the detail how it is working and how it is creating the problem in the device performance. Okay, so basically the BTI increases the threshold voltage, and that may affect both NMOS and the PMOS devices. But BTI is of two types. Either it could be the negative bias temperature instability, or it could be positive bias temperature instability. And NBTI and the PBTI, these both kind of BTI effects can observe in both the devices like PMOS and the NMOS devices. Okay, so if we can summarize, we can have four different components like NBTI effect in the PMOS transistor, NBTI effect in the NMOS transistor, PBTI in PMOS, and PBTI in NMOS. Out of these three or four components, the NBTI in the PMOS transistor is one of the serious concern, and which is more dominating one component as compared to other one. Okay, so generally people consider negative bias temperature instability effect in the PBTI, but yes, of course, we can also consider the PBTI in the NMOS transistors, but of course the magnitude is somewhat lower than the NBTI in the PMOS transistors. Okay, so generally the NBTI in the PMOS transistor is more sizable, and that is dominating component in the circuit reliability, and that we need to consider. So the NBTI becomes one of the major concern, especially if the oxide thickness is reducing less than 2 nanometer. Okay, because if the oxide thickness is very less, in that case the tunneling will be higher. So the tunneling probability will be higher. Okay, so this is how it affects. So if just we concluded like the effect of NBTI is more severe in the devices, in the PMOS devices. So let us consider what negative bias temperature instability is and how it comes into the picture in the device degradations. Okay, so the negative bias temperature instability is mainly due to two things. The first one is negative gate to source voltage, and the second thing is the elevated temperature. What it means? It means that if the potential difference between gate and the source terminal of the PMOS transistor is negative, like the gate is connected to 0 and the source is connected to the VDD, in that case the negative gate to source voltage will be there, or the potential difference between gate and source will be minus VDD. Okay, so in that case the negative bias temperature instability comes into the picture. The second one is the elevated temperature. What it means? It means that if I am operating our device at higher temperature, in that case effect of NBTI will be more. Okay, so these are the two things. So one may ask, like, if I somehow can reduce the operating temperature, then definitely the effect of NBTI can also be reduced. But in the previous slide, just I told you, if the activity factor is more, then the hot spot will be created, and if hot spot is created, then the effect of NBTI on those hotspot will be more. Okay, so this automatically comes into the picture. So we cannot control it, because if hotspot is creating, then definitely the effect of NBTI can be increased. Similarly, one more thing, like negative get to source voltage. Someone may ask, like, if somehow we can reduce this negative get to source voltage, so we can also save our device from this effect. Of course we can do that. For that purpose, what we need to do, we need to reduce the source voltage, which is VDD. So, but if I am reducing the VDD and to overcome the effect of NBTI, definitely that is going to affect the delay also, which we have already discussed in the previous slide. So if I am going to reduce the supply voltage, then that will affect on the performance of the thing. So for high performance applications, we cannot reduce the supply voltages at the lower side. We need to keep the supply voltage sufficient high so that we can get the better performance. So especially for the high performance applications, we cannot reduce the voltage. And if we cannot reduce the voltage, what it means, the effect of NBTI will be more. So this is how we can relate the NBTI with the different temperatures and with different supply voltages. Okay. So what happens? Basically, holes from the inversion layer that can tunnel into the gate oxide, and they break SiH bond, because SiH bond is the dangling bond, and which is the loosely bond, weaker bond, and they may leave some interface trap, and because of this interface trap, the threshold voltage of the device is increases. So this is the reason how the NBTI comes into the picture. But yes, there is a beauty of NBTI. What that beauty is, I will tell you. So of course, here you can see the picture. So if I have some zero gate voltage, and suppose source voltage is VDD, in that case we can observe some negative gate to source voltage, and the NBTI effect will be there. So that condition is known as the NBTI stress condition. Okay. So suppose I have inverter. Okay, so someone may ask, in practical or in any other circuit, how this NBTI we can observe. So suppose I have some circuit like this, which is inverter. Here we have the VDD, and here we have ground. So if I'm applying 0 volt here, okay, and because the PMOS transistor, the higher potential for the PMOS transistor is the source one. Okay, so source is already connected to the VDD, and if the gate is connected to 0, so if I'm applying the logic 0, in that case this PMOS transistor will come under a stress condition. Okay, so this is how this stress condition comes in the real example. Okay, now the beauty of this thing, I was saying there is some beauty of NBTI. If somehow we can change the polarity, like the source voltage is 0 and the gate voltage is VDD, or it is not necessary that the VGS is plus VDD. If the VGS is 0, in that case the NBTI conditions can be recovered. So the trapped charge can be recovered back into the oxide or at the interface, and this condition is known as the NBTI recovery. So stress and recovery, both phenomena happens in the NBTI. So stress means if I am applying negative gate to source voltage, and recovery means if the negative gate to source voltage is removed. Okay, or it is positive one, or it is 0. So in that case the recovery will come. But the thing is, someone may ask, if I'm talking about the digital systems or digital circuits, in that case 0 and 1 both logics are there. So if at logic 0, if stress is there, so for logic 1 the recovery will be there. So how it is going to affect the performance? So the answer of this question is, if I have during the stress condition, the number of trapped charges, the 100% trapped charges cannot be recovered back. Of course, some of the trapped charges can be recovered, but 100% trapped charges cannot be recovered. And because of this, with respect to time, the resultant threshold voltage shift keep on increasing, and that may lead to system failure. Okay, that we need to explain it again. So basically, so might be you will be, so you can ask the question in between if you have any question. Otherwise, you can keep posting on the chat box, and at the end, I will read all those questions and I will try to answer those questions. Okay. Now, if we talk about the NBTI, we can have the two types of NBTI. The first one is the static one, and the second one is dynamic one. Static NBTI means if we are continuously applying negative gate to source voltage without recovery. So if only stress condition is present in any of the circuit, like if I have connected the gate terminal of the PMOS transistor directly connected to the grounded, so we cannot change the gate terminal of this PMOS transistor. In that case, the static NBTI will play a major role. So the device will always be in stress condition. There is no recovery. And the second one is the dynamic NBTI, where stress and recovery, both phenomena happens. Like if we are changing the polarity of gate terminal, so we can say like some time the device is under stress, and for some time the device is under recovery mode. Okay, so this is how we can do that. So now you can get a clear picture, like if one device is under static NBTI and another device in the under dynamic NBTI, so the effect of static NBTI is more on the device as compared to dynamic one. This is simply because in the static NBTI there is no recovery, and continuously the threshold voltage is going to increase with because of this NBTI. But in the dynamic one, the stress and recovery both is happening, so the resultant change in the threshold voltage is not that much high as compared to the static one. Okay, so the static NBTI is higher than the dynamic one. To demonstrate this dynamic NBTI, so here we can see like the first phase is the stress, where the stress is coming and the threshold voltage is going to change. But on the opposite side, if the recovery phase is coming, then that change in the threshold voltage is recovered back. But if you can also observe, the 100% the threshold voltage is not recovered. Some of the threshold voltage is there. Okay, and that will increase for each time or each stress. After each stress, this threshold voltage is going to increase, and might be the timing error, or there may be some system failure after certain time period. But of course, the important thing is the dynamic NBTI will take more time to make system fail as compared to the static NBTI. Okay, so this is the thing which you need to consider. Now, one very important thing, how this NBTI, what are the different parameters on which the NBTI depends? Some of the parameters I have already told you. The first parameter is the voltage, supply voltage. Second parameter is the temperature. Third parameter is the stress time. So if I am increasing the stress time, definitely the failure will be faster. Okay, so here we can see. So suppose I have two devices. One device is having the oxide thickness of TOX, and another device is having the TOX2. And if TOX2 is lower, then the breakdown will be earlier. So the system breakdown will be earlier. So you can see these figures, like the oxide thickness play a major role in the breakdown. The defect generation or defect density also play a major role. So if more defect density is there, then the breakdown will be earlier. Similarly, if I am operating with the different supply voltages or with the different voltages, then the failure will also depend on the voltages. If I am operating at different stress time, then that also play a major role. And also the temperature, if I am using the different temperatures, then the failure will be different. So these are the some things which play a major role at what time the system will be failed due to NBTI. The first component is the oxide thickness. Second component is the defect density. Third component is the stress voltage. Fourth component is the stress time. And the fifth component is the operating temperature. So these are some of the parameters which decides what is the optimum time or what is the time of failure due to the NBTI. Okay, so might be you will be able to understand what I am teaching you. So this is all about the NBTI. So yes, of course, the VTI so because of this NBTI, the threshold voltage shift is approximately 4 times higher for each next technology generation. What it means? It means that if I have a technology generation 45 nanometer, and after 1 year, if the threshold voltage is increasing by, let us assume 10% for 45 nanometer, then if I am going to the next technology generation like 32, so for 32, it will be increased by 4%, means 14% degradation will be there. So what it means? It means that for the lower technology generation, the resultant shift in the threshold voltage will be much higher, and that can affect the performance. Okay. Here, there is one interesting thing, and might be you will be confused what I just discussed in last 10 minutes or last 10 to 15 minutes. Okay, so here one thing you need to consider, like the effect of NBTI, that includes, as I have already told you, that will increase the threshold voltage. That is perfectly fine. Second thing is, because we know that if the threshold voltage of the device is increasing, what it means? It means that the power dissipation is also going to reduce, because the leakage power dissipation flowing through, the current flowing through the device will also reduce. So leakage power dissipation will be reduced. So what it means? And the third effect is speed degradation, of course, because the threshold voltage is increasing, and if threshold voltage increases, the speed or the delay is also increases. So if we closely look into these 3 effects, the first effect is the threshold voltage increment. Second effect is the degradation of the drain current. And the third effect is the speed degradation. So NBTI effect is probabilistic. This is a problem, especially if I am considering the high performance applications, because due to NBTI, speed of the device is going to reduce, and if speed is reducing, what it means, the high performance capability will be also affected. Okay, but here is very important thing which you need to consider. Second one, here you can see degradation in the drain current. So if the drain current is decreasing, what it means, the total power dissipation is also reducing. So someone may ask, NBTI is giving some kind of benefit, especially if I am going to design a circuit for high energy efficient kind of applications. So if our application or if our objective is the energy efficiency, then this NBTI can give some benefit. So this is one of the very good thing. But of course, at the same time, the delay will reduce. Okay, so you need to compensate, or you need to compromise with the delay, but of course the energy efficiency will be higher, and vice versa. So the key point of discussion here is, if your objective is the high performance applications, in that case the NBTI is a problem. But if your objective is the energy efficiency, not the performance, in that case the NBTI can give you the benefit. So there are many papers published related to the aging benefits on the system performances. So you can go through it and you can find some interesting points from those papers. Yeah, this is the trend, how the threshold voltage of the device increases, and subsequently the leakage current also reduces, or the drain current also reduces. And because of this, as I already told you, the degradation also depends on the gate voltage. So if I am changing gate to source voltage, definitely the effect of NBTI will also be affected. So if the gate voltage is less, then the effect will be less. But if I'm increasing the gate voltage, that is going to affect the performance as well. Okay, so these 2 figures demonstrate those things. Yes, this, how much time we have, because I need to maintain the things. Okay, so it is 12:40, 30 minutes is there. Okay, fine. I think I am taking too much time to explain the things. Still, I have covered only 14 slides, and no problem. So I will try my best to finish it up. So yeah, in the previous slide, we discussed there are two types of the NBTI. The first NBTI is the static one, and the second one is the dynamic one. Okay, so in the static NBTI, what we consider, we constantly applying a negative gate to source voltage on the devices, and the device is always on stress condition. Okay, but in practical, this is not possible. Okay, whatever the digital system we have, all those digital system must have two logics. So they may have some, there may have some switching, and if there is some switching, so a dynamic kind of behavior will be there. Okay, so this particular picture explains what happens if I am going to change the duty cycle. So beta is equal to 1 means the static NBTI. Okay, so the device is always on stress. So in that case, the change in the threshold voltage with respect to time is higher. But if I am reducing the this duty cycle beta from 1 to 0.75, 0.5 and 0.25, the effect of NBTI on the threshold voltage is also very less. So you can observe from here, like the effect of NBTI on the threshold voltage is higher if the duty cycle is close to 1, and if the duty cycle is close to 0, then the change will be 0, something like that. So there will be no change if there is no stress condition. Okay, so this is how you can consider. This is also one very important thing which I have already discussed, so I will not take too much time. Delay, with the technology node, the delay is going to change, and also the leakage current is also going to change. Similarly, this is the very important thing, how the threshold voltage is going to change with respect to the due to the NBTI for the different technology nodes. So the threshold voltage is also increasing, and the delay shift is also going to increase because of these NBTI effects in the PMOS transistors. So we need to consider these things carefully. Now, this was the first degradation, which is the time-dependent degradation. Second time-dependent degradation is the hot carrier injection. Okay. Remember, the hot carrier injection is basically, if we see the bias temperature instability, occurs during a level, whatever level we have, like if the VGS is either 0 or 1, whatever it is, the BTI comes into the picture. But the hot carrier injection comes into the picture during switching from 0 to 1 and 1 to 0. So if I have some digital system, digital logic, like simple inverter, so if I'm changing the input from 0 to 1, then the HCI will play a major role in this phase. Okay, but the BTI will be there when the state of the logic is either 0 or the 1. But the HCI will be there if the state of the logic is switching from 0 to 1 or 1 to 0. Okay, so this is the basic difference between SCI and TDY. So what happens? The carriers which are present in the device, they get accelerated into the lateral field, and they gain sufficient kinetic energy. And because of that sufficient kinetic energy, they start injecting into the oxide one. So because of this one, they used to penetrate into the oxide, and because of that, they increase the threshold voltage of the devices. So this is how this hot carrier injection works. So basically, the simple difference between SCI and the TDDB is the levels at which we are operating the circuits and the phenomena. In the first one, in the BTI, the dangling bond used to break, and because of that, there is some charge trapping. But in the SCI, there is no dangling bond effect, but the charge carriers get sufficient energy and they can tunnel into the oxide. And because of that tunneling of high energy carriers, the threshold voltage is going to change. And this is how the HCI works. So this is how these two are different from each other. Okay. third and the very important thing is like time-dependent dielectric breakdown. This is really a very important thing, and that need to be considered. Before going into the detail of this time-dependent dielectric breakdown, I just want to recall something related to the material. Okay, so suppose I have some material. So the dielectric strength of the material is nothing but how much electric field strength it can sustain. Okay, so that is known as the dielectric strength. So suppose I have some dielectric material. I have applied some potential across those dielectric materials. So initially it will be the resistance will be very high. But what happens if I'm increasing the electric field across this dielectric material? Might be the conductivity of that dielectric material is also increasing. And if we are keep on increasing the electric field, then after the certain limit, it will lose its strength or the property of dielectricity, and that may start conducting some charge carriers through the terminals. Okay, so the up to the dielectric, so that is known as the dielectric breakdown. So the potential or the field at which the dielectric material loses its property is known as the dielectric breakdown. Okay, so now let us come back to the VLSI side. Basically, the dielectric breakdowns are of two types. Okay, the first one is the hard dielectric breakdown, and the second one is soft dielectric breakdown. So if I am keep on increasing the electric field across the dielectric materials, and we are intentionally forcing them to be breakdown. Okay, so this kind of breakdown is known as the hard breakdown. Okay, so this kind of breakdown is known as the hard breakdown. But if I have applied a sufficient or the nominal electric field, and if our device is working continuously, but due to some defect generation in the oxide with respect to time, we are not increasing the electric field. The electric field is the same, but due to with respect to time, there are some defects which are generated in the oxide material, and because of those defects, there is some leakage current, micro leakage current start flowing. So if there is some sufficient number of defects between the polysilicon and the silicon material, so they may form a path between the polysilicon and the silicon, and the direct current will start flowing through it. So this kind of failure is known as time dependent dielectric breakdown, because these defects are generated or these are increasing with respect to time. Okay, so this kind of dielectric breakdown is known as time dependent dielectric breakdown. In case of any doubt, you can ask the question. Okay, so this is what the time dependent dielectric breakdown is. Okay, so and this is how it is different from the, so there is a huge scope of research in this one time dependent dielectric breakdown. So it's still the modeling part is left. So the modeling of the time dependent dielectric breakdown is not mature. If you talk about the simulation side, so there is a very less results has been published related to the simulation considering the time dependent dielectric breakdowns. So you can focus somewhere here like time dependent dielectric breakdown kind of phenomena in the circuit. Okay. Okay, so this particular slide is going to be very interesting, and I'm going to summarize the things like how the aging effect at different abstraction levels. I will start it from the materials and I will close it up to the system level. Okay, so see, I have some materials. So if there is some manufacturing variability, I have some material like SiO2 here. So that there is some degradations like NBTI, PBTI, SCI, and TDDB at the physical level. Okay, so if I am talking about the physical level or at the material level, then I need to consider these NBTI, PBTI, and other things for the system reliability, or for the device reliability, or for the material reliability. But If I'm going into the more hierarchical sites, like upper hierarchy, like if I'm increasing the abstraction, so from the same material, I will design some devices. So let us assume I have designed some transistors. So the effect of this NBTI, PBTI, SCI, and TDDB, which we have observed on the material, that may affect differently in the device side. So see, these are the phenomena like BTI, SCI, and TDDB we observe at the material side. But these phenomena may affect the device performance, and what kind of performance degradation we will observe in the devices? Those are the threshold voltage change, transconductance change, and the drain current change. So these are some of the parameters which we observe at the device level due to this NBTI, PBTI, SCI, and TDDB. So if I'm considering the materials, I need to consider these things. But if I'm considering the devices, I need to focus which are the parameter is going to be affected. Okay, so the parameters, some of the parameters are like the threshold voltage of the device, transconductance of the device, drain current of the device. These all will be affected due to these physical parameters or physical phenomena. Now, if I have designed some circuits or some simple gate level designs based on these devices, so I have PMOS transistor, NMOS transistors. Now I have designed some inverter. Okay, so in inverter, I will not consider the transconductance, drain current, and the threshold voltage. But at the gate level, I will try to analyze the effect of these BTI, TDBDB, and the SCI on the performances like the power dissipation and the delay of the circuit. Okay, so of course the problem is same, but the things which we are going to observe or analyze at different abstraction level will be different. Okay, so at the gate level, I need to consider delay and the power. Now let us make some circuit level designs like SRAM. So what we know that the SRAM is nothing but if we cascade back to back two inverters, then it will become the SRAM, and then we need to connect some two excess transistors. Okay, so if I am considering two inverters and with excess transistors, let us assume that is SRAM cell. So this kind of degradation phenomena that may affect the noise margin and the critical charges. Okay, so at this level or at the circuit level, we will not consider the PBTI. We will consider the effect of PBTI will affect the noise margin and the critical charges. And similarly, if I'm talking about the system level, in that case, the same phenomena may affect in a different way. The first one could be like timing violation, data corruption. So these are the mechanisms. So the key point of consideration here is, even though we have a physical phenomena, which is the BTI, SCI, and TDDB, but at each abstraction level, this physical phenomena is considered differently. Okay, so this is the point which we need to consider. Hope you are getting interest on it. I don't know, but this is really very important to consider. Now, this is the bathtub curve. I will not take too much time because I'm some behind that time. Okay, so bathtub curve, especially system graph here. This one is the first one graph from the initial time to up to this time we have here. This, if the failure is there, like initially the failure rate is more, but with respect to time, if the fabricated chip is performing well, so with respect to time, the failure rate is going to reduce because now it is started working. Okay, but if any of the chip get failed during the initial phase, then those kind of failures are known as the infant mortality. Okay, and during this time period, if the chip get failed, so we call it defect, burn-in time defect. Okay, or we also call it early failure. But once the system is perfectly fine during the early phases, during the early analysis, then after this particular time period, the system will start working perfect. But due to time-dependent degradation, the failure rate is going to increase with respect to time. And after a certain time period, it crosses a failure rate to the limit where the system get filled. Okay, so these are the ranges where we can say the system is going to work perfectly fine, or it is the on-service region. And after this, the device or the circuit will be in the wear out condition. So system get filled. So this region is the optimum one. This is the optimum region where the circuit or system is performing well. Okay. Now, the important thing of consideration here is the wear out probability or the failure rate also depends on the technology node. So if we keep on increasing the technology evaluation, or if we keep on decreasing the technology node, so the failure rate will be faster. So the service time will also be less. Okay, if you can see here, the service time is more, but for the lower technology, the service time is less. So the service time also depends on what kind of technology we are considering. Okay, so this is the very important thing which we need to consider. So not so you can open it, and it's very important bathtub curve, explain everything very well. Okay, so apart from this aging effects, the soft error mechanism is one of the serious concern, especially if I'm operating our devices in the harsh environments. Okay, so how it happens? So if our device is placed in the harsh environments, so what happens? The high energy particle strike on the devices, and they generate secondary electron hole pairs, and those secondary electron hole pairs are collected at the most sensitive region in the devices, and the most sensitive region in the device is the drain terminal. Okay, so what happens if high energy particle strike on the device bulk? Then they create some secondary electron hole pair, and those secondary electron hole pairs are collected at the sensitive region, and because of that, there is some sudden peak current. So there is some sudden rise in the current at that particular node, and because of that rise in the current may create some glitch in the performance. Okay, so what happens? You can see here. So if the high energy particle strikes, though, so the most sensitive region, this will create some glitch like this. If you can see here with respect to time, so initially the high amplitude glitch is generated due to this high energy particle, but with respect to time, this glitch vanished. Okay, so what happens? The system will be failed in this time period. So if the system can sustain for this time period, that can work perfectly fine. So because of this can be recovered, so that is why we call it the soft error. This is not a hard error. So the question is asked, soft error and the hard error. So I will tell you after one slide. Okay, so this is how this glitch is generated, and you can observe this one. So to demonstrate this, we can consider two circuits, basic circuit like inverter. So suppose I have some inverter, okay, and the logic input is 0. So output should be high for this inverter, but due to high energy particle strike, might be there is some glitch, and the output will be shifted from 1 to 0. So output will become 0 for a short period of time, and this changing from 1 to 0 is responsible, like this NMOS transistor is responsible to create this one. Okay. Similarly, so this will be in the problem. This device is in the problem. Similarly, if our logic is 1, input logic is 1, so the output will be at logic 0. In that case, if some high energy particle strike on the devices, so the output will trigger the logic 1, and for the logic 1, this PMOS transistor will be responsible. What it means, the PMOS is under the high energy particle radiation effects. Okay, and this basically high energy particles look like whatever the glitch we are observing here, this looks like a double exponential current. Okay, and if it looks like a double exponential current, so we can model this double exponential expression. Yes. Any question? I hope you are able to device is clear. Okay, so may I continue? Dr. Rawat. So,
Yes, sir, I'm getting you.
so this is how it, yeah, what is fine now? Voice
Yeah,
is
it's
correct,
fine.
right? I'm getting perfect voice.
Yeah, correct.
Okay, okay.
Yes,
It
sir, fine,
was
fine.
some glitch in between, so that is why I interrupted. Okay, perfect.
Yeah, no problem.
So
yeah.
this is double exponential current, and that we can model. So like because the glitch which we can receive here looks like a double exponential current pulse. So here we can model the current pulse which we can inject at the drain side to analyze the soft error robustness of the circuit. Okay, so this is how we can do that one. One very important thing, someone may ask how this soft error affect the performance. Okay, for example, I have some NAND gate here, and if I am injecting some double exponential current pulse at the output of this NAND gate, okay, so double exponential current pulse will be there. So this pulse will be treated as a high pulse, and this inverter will give some low logic because of this high energy particle. Ideally, there should be no change in the logics, but because of this high energy particle, this inverter may treat this pulse, a double exponential pulse, as a trigger pulse, and that may create some low logic. And if low logic is there, and if it will pass through a different stages, might be this can act as a pulse, and that may change the logic of the flip-flops. So at the time when the particle strikes and the clock pulse is high, or if this D flip-flop is active, in that case, this glitch can act as a pulse, input pulse to this D flip-flop, and might be the data will be changed or data will be replaced. So this is how it can create the fault. But one more thing to consider, if the time of occurrence of this glitch at the flip-flop is not matching with that clock pulse activation, then it will not affect the performance. But if it is falling on the same region where the clock pulse is activating, then it will create the problem. So this is how it can affect. Similarly, it can also affect in terms of delay. So here you can see, like here we have the circuit, like if there is some the particle strike at the output of the first inverter, so the output of the second inverter will be delayed, and subsequently the output of third inverter will also get delayed. How it is happening? Let us try to see here. If you see here, normally we are assuming that the output of the first inverter will change from low to high. This is perfectly fine. But if some particle strike at this one, so because the output is changing from low to high, so this particle strike will pull back the output from high to low. So again, it will pull back to this lower logic, and this will be lower logic until the existence of that glitch. So once the glitch is removed, then again, because we have already provided the input high, so the output will again try to change to logic high. So ideally, if you see, ideally we were assuming that high will be here, but due to the soft error or the glitch, we are assuming logic high at this one, and this kind of the changes or the delay in the output logic is known as the soft delay. Okay, so this is how we can observe the soft delay in the circuit. I'm skipping this thing because we can mask some of the things, so you can go through it. Now, important thing is like how we can a very important thing to consider here is how we can embed, or how we can join the effect of NBTI with the soft error robustness. Okay, so basically the soft error robustness of any circuit is analyzed with the critical charges. If the critical charge of any circuit is high, what it means, the soft error robustness is higher. Okay, so if the soft error robustness is higher, what it means, it can sustain in the harsh environments. Okay, so the critical charge is one of the important thing that need to be considered. So here we can see, if I have the normal threshold voltage, then if the soft error probability is, let us assume 50%, then after the impact of NBTI on the device, so the threshold voltage is going to increase, and because of that the soft error probability is going to increase. What it means? It means that if the effect of NBTI is there in the circuit, then the soft error robustness will also reduce, because the soft error probability is going to reduce. But to demonstrate or to claim this statement, let us come up with some results, and you can see this result. If the critical charge of a simple inverter at 0 time without NBTI effect is, let us assume 0.77 femtocoulombs, but after 1 year of NBTI effect, the critical charge is going to reduce to this value, and after 2 years again it is reducing. What it means, with respect to time, the effect of NBTI is increasing, and because of that the critical charge is also reducing. So this demonstrates that the soft error upset probability increases with the impact of NBTI in the circuit. So this is a really very important thing that need to be considered. Now let us come to the hardware security primitives. Okay, so that is the end of the reliability issues. Now I will talk about some hardware issues and the hardware security issues, and how we can embed the hardware security primitives with the reliability concerns, and what kind of reliability concerns that can be utilized to improve the security of the systems. Okay, so there are basically 4 major hardware security primitives. The first one is the physically unclonable function. Second one is the true random number generator. Third one is the counterfeit electronic, and the fourth one is the hardware trojan. Before discussing these things, let's talk about why hardware security is important. Okay, so day by day, if we are surrounded with the electronic gadgets, like, see, but because if I am doing some transaction, in that case, if there is some trojan on it, it can be trapped, or information on the stored data can be trapped, so that this will create security concern. Okay, so we need to make our design, our system, or our circuit in such a way that the information whatever we have shared, or whatever information we have stored on the chip, that cannot be extracted. Okay, so for that purpose we make some hardware security primitives, and one of those hardware security primitive is the physically unclonable function. Okay, so let's talk one by one. So let me see what is the time, and then accordingly I will plan. So Dr. Raut, I will extend for 10 more minutes, and then I will finish, because
Okay, sir.
we started
Okay, sir.
10 minutes late. So I have tried to take 10 minutes. Right? Okay, so
Okay, sir.
So there are 4 hardware security primitives. The first one is the physically unclonable function. Second one is the true random number generator. Third one is the counterfeit electronic, and the fourth one is the hardware trojan. So let us discuss one by one. What happens before explaining the working of this physically unclonable function? Let me recall some process variations. Okay, so we know that there was inter-die and the intra-die process variations. Okay, and if we talk about the intra-die process variation, there we saw, like, if I have fabricated two devices on a single chip, on a same chip, both the device will perform differently because of the intra-die variations. If I'm considering the reliability concern, then the intra-die variation is really a problem. But that problem can be utilized as a security perspective. How it can be utilized? So here I just want to tell you. Suppose I have some design, and both the designs, even though I have fabricated both the designs on a single chip, but they will have a different process variation effects. And if they have the different process variation effect, the responses of both the devices will be different. And if the responses of both the devices are different, what it means, even though the challenge input, whatever we are providing is same, but the response for the different devices will be different. So only the authentic user will know how this device is performing for that particular challenge. But unauthorized person cannot extract what kind of response I will receive for that particular challenge, even though they know the challenge, but they will not able to extract the responses, because the variation for each devices will be different. Okay, so the only trusted person can authenticate it whether the challenge and response pair is matching with it or not. So the physical unclonable function is utilized for that particular purpose. So to generate the challenge response pair, we need to have some physical unclonable function. So this is one of the research dimensions where you can work. You can design certain physically unclonable function that can give the response which cannot be trapped. Okay, so this is really very important. One very interesting thing here to consider is, like, the process variation, which was the problem in the reliability side, and here the same process variation can be utilized as a benefit for the security concern. So this is really a very funny thing. If I'm considering the reliability, so I need to make our system with less process variations. But if I'm considering the security, so that reliability concern becomes the benefit. Okay, so here we need to connect these two things. Next thing is like true random number generator. Okay, so for any authentication we need some key. Okay, so I'm getting some noise from the background. Will you please turn off your microphone? Some noise is coming from background. Please turn off your microphone.
Please, the candidate, turn off your microphone.
Okay, thank you. So the second, the primitive is a true random number generator. So one very important thing is, ideally, we don't need any kind of noise that can present in the devices, because like the one of the well-known noise is the random telegraph noise. So the random telegraph noise affects the device performances, and this is the really a reliability concern. But if you're talking about the TRNG, true random number generation, if we have more effect of noise, more noise is present in the device, the randomness in the key generation or the number generation will be more. Okay, so here this is also really very interesting. So if you're targeting the reliability concern, in that case the random telegraph noise or the any of the noises in the devices should be as small as possible. Ideally it should be 0. But if there is some presence of the noise in the devices, those noises can be utilized to generate truly random number generation. Okay, and that truly number generation will create will be utilized to generate random keys that cannot be copied. Okay, so if if it is truly random, so the predictability will be very less. So we cannot predict what kind of key we have generated, what kind of number we have generated. But one very important thing is, if we don't have the strong or true random number generator, or the effect of noise is very less, in that case, it is very weak. And if it is weak, might be the attacker can predict whether what kind of repetition is there. If you can see here, the same kind of code is repeating again and again. Okay, so if the attacker can see the pattern of the codes, so they can assume that, okay, so some of the keys are repeating again and again, and might be this is the key, authentication key. So the attacker can now they can access the things even though they are not authorized to do that. So for that purpose, we must need true random number generator. So here is very important thing. Whatever the puff you have generated, if you embedded the noise pulses on that, noise effect of noise on that, then you can have the true random number generator, and that is utilized to create the means like which cannot be predicted. The key whatever generated we have is it cannot be predicted. Okay, so this is the importance of true random number generation. So as I already told you, the noise, which was the problem in the reliability, becomes the benefit in the random number generations. Okay. Now the third thing is like the counterfeiting. If we are the end user, we used to throw our e-waste, and then people used to process it. Because whatever the e-waste we have thrown on the garbage, all the components are not waste. Some of the components are still live. So what people do, they used to recycle it, and they again send into the global market, and then it comes to us again. So these kind of problems are known as the counterfeiting. Okay, so how the counterfeiting can be included on the supply chain? So the counterfeiting could be like during the design time, where the clone or the tempered design is inserted while designing. So someone other can access the cloned one, not the original one. So this is one kind of counterfeiting. If you go to the fabrication side, if you are fabricating, like they have fabricated over, like they got the contract to fabricate like 1 million component, but they have fabricated 1.1 million components. So this is also one kind of the counterfeiting. Now rest 0.1 million component, they will resell it without any information. So this is also one kind of the counterfeiting. They have the defective or the tempered designs while the fabrication. So if they are fabricating and they have tempered some of the components, so this is also one kind of the counterfeiting. If you go to the assembly side, so on the assembly, they can overproduction is fine, but out of specification and temper is also one of the, like fabrication and assembly is same, like they have done something, this kind of manipulation, and that is this is the problem in the supply chain of the electronic components. Similarly, while distribution, there could be some counterfeiting. While lifetime, this is really a very important thing. So if we talk about all the supply chain components, this is really very important. The people used to recycle it. So see, if they have overproduced, this is not a problem, even though they are giving you the authentic key, means the right key, chip, which is working perfectly fine. But somehow, if they have inserted some recycled item and they are selling it like a fresh, so this is the problem. Remark, like whatever the original thing is there, they have to remark, they remark it and they are reselling it again. They are selling like out of specification chip. So these are some of the problems which are really very important to consider in the counterfeiting. And similarly, but the question could be like how we can utilize or how we can check those counterfeit ICs. So now, very important thing here. I'm just explaining one more thing. How we can detect the counterfeit ICs. Okay. So the simple thing is, if you can recall my NBTI things, at that time I told you due to the NBTI, the leakage current is reduces, okay, and the threshold voltage increases. So with respect to time, the threshold voltage is increases if the device is under stress, and if I am doing it the recovery phase, then the threshold voltage recovered, but 100% threshold voltage cannot be recovered. What it means, if I am using used IC, the specification will never match with the new IC because there is some permanent shift in the threshold voltage. Okay, so the NBTI, so I have two chips, one is the used one and one is the fresh one. So the current flowing through the used one will be different than the current flowing through the fresh one. So if somehow we can compare these two things, then we can check, yes, this particular IC is the counterfeited and this one is the fresh one. So the important thing is and the funny thing is the NBTI was the problem, but for the security perspective, NBTI becomes a tool to detect the recycled IC. Okay, so so the reliability and the security, these two are really interrelated to each other. One of the parameters is problem for one particular thing, but it becomes the benefit for other part. Like if it is problem with the reliability, then it becomes the benefit for the security and the vice versa. Okay. And the last one is the hardware Trojan. So hardware Trojan means if someone has inserted unwanted components during each of these stages, so this kind of the security concern is known as the hardware Trojan. Like suppose I have the idea, I have the trusted idea, but intentionally they have made some mistake in the specification design. So this is also one kind of the Trojan. At the HDL side, like they have some design which are the tempered one. They have inserted the HDL which is the tempered one. So there is also one the probability of Trojan here. They have used some IPs which are the not good. So this is also one of the things where the Trojan can be there. Similarly, you can have, you are utilizing the manipulated tool for the synthesis, for the mapping, for the placing and the routing. So if we are using some manipulated tool, so this is also the part of the hardware Trojan. Similarly, for if you are talking about the FPGA, so there could be like configuration file loader and FPGA, there could be some problem. And if you are talking about the ASIC, there could also be the problems. Okay, so the hardware Trojan can be inserted at any of the stages. Okay, and these are the unwanted section which we are going to insert. Okay, and we need to detect it. Okay, so this is also one of the research dimension where you can consider. So for example here, so suppose I have fabricated some chip, but intentionally someone has added this additional wire between two components. So this is the nothing but this is the Trojan. Okay, someone has cut down some of the wires. Okay, so this is also one of the Trojan. So the Trojan is nothing but if we are manipulating intentionally into the design specification, so those are, we call it the hardware Trojan. Okay, and we need to detect it properly. Now let us coming to the end. The first one is so what are the different reliability challenges which we need to consider? Okay, so if I'm considering the reliability challenges, so basically based on the ITRS report, the reliability challenges are considered into two terms. The first one is the near term and the second one is long term. So near term is the reliability concern which we are currently facing, but the long term reliability challenges which we are going to face in the future, and that need to be considered. If you are talking about the near term reliability concern, so currently the TDDB, NBTI, PBTI, RTN, SCI, all these are the important points which need to be considered in terms of the reliability. Similarly, gate to contact breakdown is also a serious problem nowadays, and yes, the statistical variation for the non-planar devices is also a very important thing. See, whatever the model the people have developed, they have developed for the planar devices, but for the non-planar devices, we need to have some reliability model that can predict the threshold of the degradation in the device performances. So this is also one of the research dimension which we need to consider in the near-term reliability concerns. Similarly, 3D interconnect reliability challenges is also one of the serious concern. Reduce reliability margin and understanding the performance in the circuit level as well is very important. So people are considering the reliability at the device level, but to understand the reliability on the circuit level and the system level is also very important. And this is the near-term problem which we need to consider. People have started analyzing the reliability for the circuit performances, but yeah, it needs to be mature. Similarly, like embedded electronics that need to be considered, like reliability of this electronics is also very important and that need to be considered. If we talk about the long-term reliability issues, so the very important thing is the reliability of new material is very important, because whatever the devices we are making, that is made of the materials. So if we have designed some material which is more reliable, then we can have the more reliable systems as well. So the reliability of material is really a very important thing that need to be considered for both the transistors and the interconnects. Reliability shifting towards the system level is also very important. Currently, people are dealing with the circuit reliability and the device reliability, but system level reliability is also a very important thing that need to be considered in the long term. And muon induced soft error rate is also very important. Muon means this is also one of the charged particles, just like electron, having the negatively charged, but with a higher mass. So this kind of charged particle may affect the performance, especially in the harsh environments. So these are some long-term reliability issues. Let us coming to the security concern. I have already told you many things, like the if I am designing the logic circuits, so the process variation is a problematic. It should not present. But for the PUF designing, the process variation is becomes a benefit. Similarly, for the TRNG, it becomes a benefit. Noise is unacceptable, especially in the logic designs and the PUF designings. But for the TRNG, noise becomes one of the benefit that can give you the more randomness. Similarly, if we are talking about the counterfeiting, so the aging effect like NBTI is problem for all other things, but for the counterfeiting, to detect the counterfeit ICs, the aging becomes the benefit. So the objective to show this slide is to interrelate the reliability and the security both. So this is how we can relate. Yes, this is nothing but this is the pictorial representation and the connection of reliability and the security concern while designing. Okay, so the process variation is unacceptable in the reliability, but for the security, this is acceptable, and other things are also included over here. So that's it from my side. So thank you so much for attending the talk. So if you have any questions, definitely you are free to ask the questions. I think I have finished on time. No,
yeah. Thank you, sir. Participants, any query from your side, you can directly ask, or you can use your chat box also.
Good afternoon, sir.
Yeah, good afternoon. Yeah, please.
My name is Pavan Kumar, sir.
Yeah, please.
Sir, actually, I am doing on single event upset mechanism, sir. You told that NBTI will also impact on single event upset by reducing the critical charge. You told like that, sir.
Yes.
Sir, if we use an high K dielectric material with a metal gate, may it will reduce this NBTI, sir?
Yes, of course, it can reduce. See, I had just referred the bulk material, right? But the soft error robustness in any of the devices, that depends on what kind of material we are using. If I'm using the high K, the problem will be reduced. And of course, if we are using the SOI structure, silicon on insulator structure, in that case, the soft error robustness is further improved. So it completely depends on what is your objective, and based on that, you can choose the materials accordingly.
Okay, sir. Okay, thank you.
So if your target is like soft error robustness, better I will suggest you to consider the SOI structure, either FDSOI or the PDSOI, and that will give you the better performance in terms of the soft error robustness.
Okay, sir.
Yes.
Thank you.
Any further questions or any doubts from audience side? Okay, fine. So I think, sir, there is no questions now from the participant side. So
Okay,
yeah,
fine.
thank
So
you very much.
I have one
Yeah.
more thing, because I am conducting one FDP on the same set like Atal FDP. So if you are interested to go into the more detail of the reliability in the security, definitely you can do register, because it is going to start in the next week only, from 2nd of August to 6th of August. And that will be focused on the reliability and the security in detail. And the experts from the abroad industry and the IITs and IITs will be there. So you can consider these things. Thank you.
Okay. Thank you, sir.
Yeah.
So yeah, thank you very much, Dr. Ambika Prasad, sir. Sir already discussed regarding the particular reliability and security issues in the VLSI circuits and systems, and mainly he has focused on the particular PBT, that is your process voltage and temperature variations, all these things, and also we discussed regarding the random number generators and also the reliability research regarding the particular topic. Really, it is a
Yes.
practical topic for the research point of view. Those are interested, those are already working on that. You can also focus on particular discussion, particular topic also, or you can also directly contact by mail to the Ambika Prasad sir, or in doubt anything. So thank you very much.
Yeah, I just wanted to include one thing, because see, nowadays reliability and the security of the systems becomes a really serious concern, and
Right.
this is really becomes a hard topic for the researchers. So yes, you need to consider the reliability and security for your research, and this is really very good research direction. And in
Exactly.
case of any doubt, definitely you can write email to me. I will try my best to support you in any of the way,
Yeah. Thank you
either
very
in the
much.
finding the research problem or in the any of the things. Definitely you can contact me.
Fine, sir.
Yeah.
So okay.
Okay,
So yeah.
so thank you so much.
Thank you very much, sir. Once again, sir, I will contact you offline.
Sure.
Yeah.
Thank you.
Thank you, sir. Yeah.
So may I leave now?
Yes, sure, sir.
Okay, thank you so much.
Thank you very much, sir. So all the participants, thank you very much once again, and again we'll join exactly at 3:30 for the next session number 6 by Dr. Ajit Kumar Panda, sir. So thank you once again.